Hello, welcome to today's lesson on colligative properties. The question of the day, what is the reason for putting salt in water when making pasta, aside from flavoring? And what is the reason for putting salt on icy roads in the winter? First up, just a recap on what happens when things dissolve. So when solids are dissolved in water, they have to wiggle in between the water molecules, and they're going to take up space when they do that. So here we have a water molecule. The O is very negative with its two lone pairs, and that is going to be attracted to positive ions that are soluble in water. The positive hydrogens are going to be attracted to the negative, also repelled by the positive. Negative ion here, attracted to the hydrogen, attracted kind of sort of to this positive here, and that's how the ions are going to arrange themselves. Now, when we're trying to boil this water with a bunch of salt in it, these ions are going to kind of get in the way, the dissolved particles. I shouldn't just say ions because it's also true for really any dissolved particles. But when we have dissolved particles, they sort of get in the way of water being able to evaporate during its boiling. This means that our water is going to have a little bit of extra thermal energy in order to push past all of these dissolved particles, which means that when we dissolve stuff in water, the boiling point of water has to rise. We need more thermal energy to get that water to actually be able to push past those dissolved particles and evaporate. The opposite is true kind of when we're trying to freeze stuff. So when we are trying to remove heat from water and get the particles to freeze, they're going to freeze nice and organized. And when this happens, remember, water is a polar molecule. It tries to line up its charges nicely as it's freezing, so that when they lock in place, they're feeling happy. Your oxygens are going, remember, they're negative. Those oxygens with the partial negative are going to try to line up near hydrogens that are partially positive. So that's what we're trying to do when we dissolve, when we freeze. But when we have dissolved particles, those dissolved particles kind of get in the way and make it hard for the particles to feel the attraction toward each other. So in this case, water is going to have to remove extra energy to slow down the particles even more so that they kind of have the power to reach across the dissolved particles and lock in place and freeze comfortably. For this reason, the freezing point of water, or really any substance, when you have dissolved particles, is going to drop. Last thing here is vapor pressure. Anytime we have stuff dissolved, the vapor pressure has to change. When water is trying to evaporate on its own, the water particles or the water molecules are trying to push up against the atmosphere in order to join the atmosphere. The pushing is their vapor pressure. When this is happening, of course, if there's dissolved particles, they're kind of in the way of the water molecule's ability to rise up and evaporate. So for this reason, the vapor pressure of water is decreased. It's lowered. And this is because water is having a difficult time evaporating. And in case you don't remember, vapor pressure is the willingness of a substance to evaporate. I will link the whole video I did on vapor pressure in the description. But water, of course, we know puddles dry on their own. Water wants to evaporate. Not that much, because water has pretty strong hydrogen bonds holding the molecules together. But when there's a bunch of like junk in the way, a bunch of dissolved particles, water has an even more difficult time evaporating. So in that case, water will have an even lower desire to evaporate. And that's just because it's way more difficult now. So like I said, vapor pressure is the willingness of a substance to evaporate. And if we have a bunch of particles blocking water's ability to evaporate, it is going to find that to be a more difficult process, and hence the vapor pressure will drop. The change in boiling point, change in freezing point, and the change in vapor pressure based on dissolved particles are called colligative properties. The degree or severity of the colligative property is going to change based on the number of particles that are dissolved. And the way I like to describe colligative properties is that the liquid phase expands. I'm going to explain that in just a second. But the more particles we have dissolved, the greater this effect of the boiling point rising, the freezing point, and the vapor pressure falling. Looking at the number of particles, it's important to remember that when an ionic compound dissolves, it dissociates into its ions, and each ion is going to count as its own particle. So if we had sodium chloride dissolve, the sodium ion and the chloride ion would count each as a particle, resulting in 2 particles. Covalent bonds, or things with covalent bonds, molecular substances, don't dissolve normally in water, so their molecule is going to stay intact, and that'll count as just 1 particle when we are considering dissociation. Here's the visual. When you have pure water, the boiling point is 100 degrees Celsius and the freezing point is 0 degrees Celsius. So this blue box here represents the liquid phase. Anything above this is going to be a gas, and anything below it is a solid. Once we go and we add solute, anything really, to water, it makes it more difficult for the water to boil. It makes it more difficult for the water to freeze. And in this case, the liquid phase kind of expands. So now our boiling point might be 105 degrees Celsius, and our freezing point might be -5 degrees Celsius. So when it comes back to the question of the day, cooking pasta, if you add salt to the water is going to boil hotter. If you add salt to an icy road, the freezing point is going to drop, meaning that if your atmospheric temperature, let's say, is, I don't know, -2 Celsius, then obviously you would have frozen ice all over the road, but sprinkling this salt on top of it is going to drop the freezing point, meaning that water wants to freeze at -5 instead of -3. -3 at that case would be a liquid temperature for water with the added salt. So it's a safety thing. It helps to melt the ice down into liquid so that the roads aren't so slippery. And this expansion of the liquid phase is a pretty good way to remember how these colligative properties work. Your boiling point is going to rise because it is more difficult to boil when there's other particles in the way. So water needs extra energy to boil, and water has a harder time freezing when there's extra solute around because those particles get in the way of the particles locking nicely into place. So your solid phase is going to drop lower as the liquid phase expands. The number of particles involved here is going to matter. So if you were trying to dissolve, let's say, sugar, sugar counts as 1 particle. Let's just pretend it's glucose, C6H12O6. All nonmetals, meaning you have a covalent bond, or rather lots of covalent bonds. Those covalent bonds will not dissociate when they are in water. So the carbons are not going to break apart from the hydrogens and the oxygens. You can get, your sugar crystal to break apart into tiny sugar molecules, but the molecule itself won't break, meaning that that'll count as 1 particle. If you had the same amount of, let's say, sodium chloride will dissociate. So you'll have sodium ions and chloride ions. So you would have 2 particles per volume or per mass, however you measured it. Meaning that in this liquid phase expansion, the sodium chloride breaking into 2 pieces will have a greater stretching of the liquid phase than sugar does, because the sugar, again, doesn't break apart. If you had potassium sulfide, whose formula is K2S, and you dissolved that, you would have 2 potassium ions and 1 sulfide ion. So that would break into 3 particles, and you would have an even more dramatic stretching of the liquid phase compared to sodium chloride, because it has 3 particles to sodium chloride's 2. That's it on colligative properties. We will do a lab experiment on this, so stay tuned for that. Make sure to subscribe so you don't miss it. Please leave any questions you have in the comment section below the video, and I will see you in the next one. Bye.